Okay, welcome everyone to today's exercises, and today we're going to run through the exercises of chapter 8, or at least 4 of them. And chapter 8 is on game theory. So we have 4 exercises, 8.1, 8.3, 8.4 and 8.7. And in exercise 8.1 you get the first exercise which asks you to solve for the mixed strategy Nash equilibria using a simple payoff matrix. And there's one disclaimer: things are made a little bit easier for you here because some of the strategies are ruled out by the maker of the exercise. And I will show you when we get to it. So exercise 8.1 is about player 1 and player 2. And each of the players has 3 possible actions or strategies. And in exercise 1 you need to find the pure strategy Nash equilibria, if any, because it can happen that there are 1 or more Nash equilibria in pure strategies, but it can also happen that there is none. And in exercise B asks you to find a mixed strategy Nash equilibrium. Well, we know for this type of games there's always a mixed strategy Nash equilibrium. And then in C we need to compute the expected payoffs for the equilibria found in part A and B. And then the book also contains exercise D to draw the extensive form of this game, but we will skip that sub-question, also because in the next question we will deal with the extensive form of a game. So you will get your practice. So find the pure strategy Nash equilibria, if any, and this asks us to find the best response for, say, player 1, given what player 2 does, and the optimal action by player 2 given the action of player 1. So we look for the best response functions, and in this case they look as follows. So if we consider player 2, what is optimal for player 2 to do, conditional on any action by player 1. Well, if player 1 chooses action A, then the best response by player 2 is to play E, because then he receives a payoff of 8, which is more than the 6 that he would receive if he would play D, or the 0 that he would receive if he would play F. So, just to remind you, in payoff matrices like this one over here, the first entry denotes the payoff to player 1, and the second one denotes the payoff to player 2. So, conditional on action A, we look at the second entries and look at which one is the highest, and in this case it turns out to be 8. So, given that player 1 plays A, it's optimal for player 2 to respond by playing E. If player 1 plays B, then likewise it's optimal for player 2 to play D, and conditional on player 1 playing C, it's optimal for player 2 to play F. And then we also consider player 1. So what is optimal for player 1 to do, conditional on a given action by player 2? Well, given that player 2 plays D, it's optimal for player 1 to play A, because that will give him a payoff of 7 instead of the 5 or 0 that he would receive if he would respond by playing B or C. And if player 2 will play E, it's optimal for player 1 to play B. And if player 2 plays F, the optimal response by player 1 is to play C. And doing all these lines under the payoffs, we observe that there's one entry in this matrix where we now have 2 bars, and that's the entry with the payoff for 4, corresponding to the actions C by player 1 and F by player 2. And this is our Nash equilibrium. So we have one Nash equilibrium in pure strategies, and that Nash equilibrium is CF. So if you are asked to write down the Nash equilibrium, always write down an equilibrium in terms of equilibrium actions, what players do. So CF. Don't write down your answer in terms of the payoffs. So you should not write the pure strategy equilibrium of this game is 4-4, because in this case 4-4 is unique, but it may also happen that 4-4 corresponds to other combinations of actions in the matrix. So 1 it's not unambiguous, or at least not always. And second, you are asked to write down a strategy equilibrium. And a strategy equilibrium is really about what players do, so the actions they take in every stage of the game, and it's not about what they get paid, about their return. So always write down your equilibrium in terms of strategies. Okay, so and why is this a pure strategy Nash equilibrium? Well, by definition, conditional on what the other player does, that the other player sticks to the action, it's optimal for the player that we consider to take the action as given in the equilibrium. So conditional that player 2 plays F, it's optimal for player 1 to play C, and he has no incentive to deviate from his optimal response. And of course, the same holds for player 2. Given that player 1 plays C, it's not player 2 is not better off by deviating by choosing a different action than action F. Now, in this case, the payoff to both players is equal to 4. And this completes question A. In question B, we step it up. We need to find the mixed strategy Nash equilibrium in which each player randomizes over just the first two actions. And this is where at the start I mentioned that this exercise is simplified, because now the designer of the exercise tells you that you only need to consider actions D and E for player 2 and actions A and B for player 1. So we can drop the part of the action space that corresponds to actions C and F. And this simplifies the game. But also in problem sets and in other exercises, this simplification may not be made, and that means that you need to consider a wider range of possible mixed strategy equilibria. But in this case, we know that for the equilibrium that we look for, both action C and action F will be played with probability 0. So PC and PF are identical to 0. Now, for player 1, we denote the probability that this player plays A with PA. So PB is that the 1 minus PA, the chance that he will play action B. He will not play C, so that makes PB equal to 1 minus PA. And for player 2, we will denote the probability that he will play action D with PD. And PE is 1 minus PD. So now player 2's expected payoff from playing D is identical to, well, it will depend on whether player 1 will play action A or B. And we don't know what player 1 will play, but we know that he will play action A with probability PA and action B with probability PB. So we write player 2's payoff as an expected payoff, taking into account these probabilities. So with probability PA, player 1 will play A. In that case, player 2 will receive 6. And with probability 1 minus PA, player 1 will play B, in which case player 2 will receive 8. So the expected payoff, if player 2 plays D, is this expression over here. Likewise, if player 2 plays E, the expected payoff of player 2 is PA times 8 and 1 minus PA times 6. Now, in equilibrium, player 2 needs to be indifferent between either playing C or D. So the probabilities PA need to be such that they make player 2 just indifferent between choosing action D or E. If we would have a strict preference for one of the two actions, then we would not end up in a mixed strategy equilibrium. So we know that in a mixed strategy equilibrium, it needs to hold that this expected payoff is identical to this expected payoff over here. So we equate the two and we solve for PA. So we equate the two, then we solve for PA, and we find that in the mixed strategy Nash equilibrium, PA is equal to 1/2. Now we're halfway, and in order to find the probability PD, with which player 2 mixes between D and E, we use the same procedure, but now we look at the expected payoff of player 1. So for player 1 will only be willing to randomize between actions A and B in equilibrium if they deliver him or her the same expected payoff. So this is the equation that needs to hold in equilibrium, and the expected payoff from playing A is identical to 7 if player 2 plays D, which happens with probability PD, and 5 if player 2 plays action E, which happens with 1 minus PD. And if player 1 plays B, the expected payoff is equal to 5 PD plus 7 1 minus PD. We equate the two, and we can now solve for PD. So, and doing that, we get that PD is equal to 1/2 as well. So that happens here, well, not fully by coincidence. If you look at the payoff matrix, you can see that the payoffs are completely symmetric. We have 7, 6 over here, 7, 6 over here, and off diagonal we have 5 and 8. So in equilibrium, in the mixed strategy Nash equilibrium, both players will mix each with probability 1/2. Why is this a Nash equilibrium? Well, given that the other player mixes with probability 1/2, you don't have any incentive to deviate and choose a different probability of mixing of 1/2. And this holds for both players at the same time. And that concludes question B. And then we have question C. So we need to compute the player's expected payoffs in the equilibrium found in parts A and B. Well, we already know that the payoff in the equilibrium, the pure steady Nash equilibrium in question A is equal to 4. And in question B, we just plug in the equilibrium values of PA and PD into the expected payoff function. So we observe that the payoff of player 1 is equal to 7, and the payoff to player 2, the expected payoff is equal to 6. And that completes question C.